Hello, my name is Ethan Hunt, and today I will be talking about phase estimations application in QRAM. It is important to understand what phase is in the quantum context. So when a quantum state has two different amplitudes, so let's say a qubit, it can be in either the 1 state or the 0 state. When a qubit's in superposition, it can be in both at the same time. It is a linear combination of the two states. Now, that doesn't necessarily mean the two states are both have an amplitude, positive amplitudes. And what I mean by amplitudes is I mean the probability that when we look at the state, what it's going to collapse to. Is it going to collapse to 0 or is it going to collapse to 1? In the case that it's 0, we might have a positive amplitude. But in the case that it's 1, we could have a negative amplitude. And these negative values, they don't really matter in the grand scheme of things. But they do tell us a little bit about the quantum state. And the negative value, in this case that I'm talking about, is actually what's known as the phase factor, or the global phase of the qubit. And this global phase is normally indistinguishable. Like it has no real bearing on the amplitudes, as the amplitudes squared become their probabilities. So a negative value, when you square it, it's going to become positive. Obviously, a positive value when squared, it's going to stay positive. So then what's the point of phase? And if we can't really see its impact on the quantum state, then how do we measure it? Well, there exists a clever algorithm to do that. To get a global phase, or just phase in general, a quantum phase estimation algorithm or subroutine must be used. And this essentially goes about applying phase kickback and applying it to many different qubits, and then applying a inverse quantum Fourier transform, and we then measure that. This measurement is then taken and converted back into the value of our phase. Now we can get back the phase as 100% of the time, like a 0 error. So it's not an estimation, it's the exact value, given that we have enough qubits. Most contemporary uses of the quantum phase estimation algorithm are as subroutines in other algorithms, like Shor's algorithm. Now, my research instead focuses on using phases as a type of temporary storage. Because phase is just a real number, and all real numbers can be approximated using a finite set of bits, it stands to reason that we could create an algorithm that maps a string to a phase. And because we know how to create a unitary operator that applies this phase to a qubit, and that then we can approximate this phase of this qubit using the quantum phase estimation algorithm up to an arbitrary level of precision, and even get back the entire phase correctly, given we have enough qubits, it stands to reason that this is a type of temporary storage in which we are storing some information in the phase of a qubit. If we were to convert a binary string to a phase outright on the 0 to 2 pi interval, there's a chance that we could lose information. Thus, we use this method of converting a string to a phase in which we are ensuring that our decimal points will always land us in the interval 0 to 1. Now that we've discussed how we can use phase as a temporary form of storage, it stands to reason that we can actually send messages using a single qubit. By storing a string of bits inside a phase of a qubit and sending that qubit over to another party, the other party can then decrypt the qubit's phase, thus transferring the message over. And this only uses one qubit to send the message. Another potential benefit of storing information inside a phase is that it can be used as an adaptable form of RAM of the system. Consider that we want to store two processes in memory instead of having them stored on a disk, as we know the I/O operations of reading and writing off a disk are much longer. So a phase can store in one qubit an entire instruction set of a program, a state of a CPU, and several other things. This is just one of the many potentials that can be unlocked by using a phase of a qubit as a temporary form of storage. So far, what we've discussed is only on the theoretical side. And to showcase a proof of concept, I created an experimental design or toy model of storing information inside of a phase of a qubit. I used IBM Quantum Simulation Lab and was able to replicate this effect. And it turns out on the standard simulation that which has no noise in it, I was able to recover the string 100% of the time in its entirety. In order to actually realize this concept, more research in quantum decoherence of qubit states and noise reduction / fault tolerance in quantum computers needs to be done. So error correction codes and etc., which are very difficult to implement on a quantum computer. That said, if there ever is a time when we can actually accomplish this, this can have many large-scale impacts as far as message passaging and potentially adaptable RAM of the system. Thank you. This has been my project.